us for this webinar on optical waveguide simulations presented by comsol. Comsol is a global provider of simulation software for product design, engineering, and research in technical enterprises, labs, and universities. This website is hosted by SPIE in support of everyone who needs to model the interaction of physical systems with light. Today's webinar will focus on periodic physical systems. We've been amazed by the interest and response to this session, and we are so glad that you're able to join us. Our webinar today will have one speaker who will present for about 45 minutes. Questions from the audience will be taken afterwards, and I encourage you to take advantage of that time to get your specific questions covered. Before I hand it over to our speaker, I'd like to go over a few housekeeping items with you. As questions are relevant to the presentation come up, please put them in the QA section of Zoom. The QA section has some specific features that make it easy for our presenters to use. For technical issues while viewing this webinar or questions about the format, please use the chat feature. SPIE staff is monitoring chat and will respond if you have difficulties. And of course, please use the chat to say hello to people and introduce yourselves. Make sure all of our chats and questions follow our digital event code of conduct, a link to which you can find in the chat now. Today's event is being recorded and will be available shortly after the event. Watch for an email from SPIE with the link with the recording. Now it's my pleasure to welcome our speaker today, Ulf Olin. Ulf is a product specialist within the electromagnetics group at comsol. Before joining comsol in 2011, he worked in optics research at the Institute of Optical Research in Stockholm and in optics fiber optics research for various companies. He's also an associate professor and docent of physics at KTH in Stockholm. Ulf, welcome.
Thank you, Bonnie, for the nice introduction. So, welcome everyone to this webinar on optical waveguide simulations. So today I will introduce you first to comsol multiphysics and especially the wave optics module. After that, I will introduce you to a few types of different waveguide simulation techniques. We will have a short demo demonstrating how to do mode analysis using comsol. And at the end, I will show you a few more examples of optical waveguide simulations. So comsol is a multiphysics software tools. And what that means is that you can combine many different types of physics. So for instance, you can combine electromagnetics with structural mechanics and acoustics. And you can also include fluid mechanics, heat transfer, and even chemistry. And furthermore, you can add your own equations that are applicable for your application. And there are also additional multi-purpose functionality, like for instance, optimization, or if you want to interface comsol with other software tools like MATLAB, Simulink, Excel, and many different CAD tools. So you use these different physics or physics interfaces, as we call them, and you build a model using the comsol model builder. So now that you have your model, then you can use the application builder to build a simplified user interface that wraps your model into an application. And in this application, you can also have special purpose graphics and reports. And what is nice about these applications is that you can let your colleagues or customers run these applications either on a server or as standalone executables. So when you use comsol, you start with the comsol multiphysics, the platform product. And then you add additional products that are suited for your particular application. For instance, from this electromagnetics category, we have the AC/DC module for low frequency simulations. If you want to go for full wave high frequency simulations, you have the RF and the wave optics modules. If you want to do ray tracing, there is the ray optics module, and then there are the special modules for doing plasma and semiconductor physics. But as you see, you can combine these electromagnetics modules together with other physics from fluid and heat transfer and structural mechanics and acoustics and even chemistry. And then there are the multi-purpose modules that I mentioned, the optimization module, the particle tracing module, and then all the different modules that you can use for interfacing to other software tools. So when discussing the modeling of electromagnetic phenomena, it is useful to divide the different types into the frequency content of your application. So we use the AC/DC module for modeling low frequency applications, like for instance, power engineering, the design of electrical motors. But if we want to model wave propagation and high frequency applications, then we are using the RF and the wave optics modules. So these two modules, they are very similar, but they have different target applications. So the RF module is targeted towards RF and millimeter wave engineering and antenna design, whereas the wave optics module is targeted towards wave propagation in optical devices and applications. Then, if you have large systems compared to the wavelengths or complex geometries, it can be more efficient to do ray tracing, and then you can use the ray optics module instead. So now, what do we mean when we say wave optics? Well, we mean full wave electromagnetic simulations at optical frequencies. And with optical frequencies, I mean frequencies in the terahertz regime, from a few terahertz to hundreds of terahertz. But we optical guys, we don't like to talk about frequencies. We prefer to talk about wavelengths. And then we say that we work with applications in the nanometer to the micrometer range. Now, another characteristic of optical application as compared to RF applications is that optical components are often very much larger than the wavelengths. So take, for instance, a semiconductor laser. It can be hundreds to thousands of micrometers long, but still it emits a light at around 1 micron. Or as you see in the pictures here, we have a directional coupler. The length of this device is a few millimeters, but the wavelength of the wave that propagates through this structure is also of the order of a micrometer. So wave optical applications, here we have to handle the situation when the simulation domain is often much larger than the wavelengths. Now, in the wave optics module, we have 5 different physics interfaces. The 3 physics interfaces to the left, they are all doing frequency domain physics. So here we solve for 1 frequency at a time. The final 2 to the right, they are useful for time domain simulations. Now, the first physics interface, the frequency domain interface, it is a general purpose interface that is very good for simulations on domain sizes that are not that much larger than a wavelength. So we use it for mode analysis, scattering, periodic structure problems, for instance. Now, if you want to simulate larger domains, then you should go for the beam envelopes interface instead. Here you will have to make a guess of what will be your characteristic wave vector for your problem. It can sound difficult, but for most problems, it's not difficult. But if you can make a good guess of that characteristic wave vector, then instead of solving for the total electric field, we solve for the electric field envelope. So then we can use a much coarser mesh, which makes it possible to solve for much larger domains. I will tell you more about this beam M-loss method later in this presentation. But we use it for wave propagation applications and for applications involving Gaussian beams. The boundary element interface is different from all the other interfaces because it uses the boundary element method. And what is interesting with this method is that here we don't add unknown variables in the domains. We only add them to the boundaries. So with the boundary element method, we don't need to do domain meshing, which can be advantageous for certain applications. The main difference between the two time domain interfaces is that the transient interface uses implicit time stepping, whereas the explicit interface uses explicit time stepping. And I would say that the transient interface is the more general purpose, the easy to use interface. So when you start doing time domain modeling, you should start with this interface. But if you know that your application will be very, very large, then you could go for the time explicit interface because it scales better for very large problems. So now that I have introduced you to comsol multiphysics and the wave optics module, let's start talking about optical waveguide simulations. And we will start by discussing how you can build your optical waveguide structures from waveguide parts. So within the wave optics module, there is a part library. And you can, in that part library, there are waveguide elements for 3D and 2D structures, for instance, rectangular and slab waveguide parts. And the different types that are included are straight waveguides, tapered, bent waveguides, S-bent waveguides, and other coupler types. And to the right here, you see a bent waveguide structure or waveguide part. Now, the good thing with these parts is that they are fully parameterized, so it's very easy to change the dimensions of these parts. And furthermore, you get some predefined selections. So you can, using these selections, you can specify what will be the core of my waveguide and what will be the cladding of my waveguide. And you can also use them for specifying the boundary conditions that you want to use for your physics simulations. And furthermore, you can use the selections for defining and building the mesh in your problem. Another really nice thing with the waveguide parts, and especially for the 3D waveguide parts, is that they actually more or less snap together when you add different parts. Because for the 3D waveguide parts, we have input and output work planes at the input part of your part and at the exit of your part. And then you can say that you should snap the input work plane of one part with the output work plane of the previous part. So building such a waveguide structure is more or less like building with Lego bricks. Now in this particular example, we have used S-bent directional coupler parts and straight waveguide parts. And you see a directional coupler down here and another one up here. And then we have connected these directional couplers using straight waveguides like this. So now, having discussed how you build the waveguide structure, we will talk more about one type of waveguide simulation, which is mode analysis. So here we will solve for the mode fields and the propagation constants. So again, what you see here is the total electric field. We say that the total electric field is the mode field times an exponential phase factor where you see the propagation constant beta. And what you solve here mathematically is an eigenvalue problem where the eigenvalue is the propagation constant and your eigenvector is the mode field. And typical applications is that you solve for the modes in an optical fiber or the electric waveguide. And you can also do simulations of anisotropic waveguide structures. So a very simple optical waveguide structure is a step index fiber. So in the Wave Optics example library, we have such an example model where we in the first part make a mode analysis for a straight fiber. Whereas in the second part of this example, we do an a mode analysis simulations for a bent optical fiber. So now it's time to make a quick demo of this step index fiber bend model in comsol. So here you see the comsol GUI. So to the right here you see the model builder window. And with the model builder you build up your model in a tree-like structure. So you define some model components, and under that you define the geometry, the materials, the physics that you are working with, and your mesh. And you also define the studies, and at the end here you find all the result nodes, the graphics output from your simulations. Now, this model, as I said, it consists of two parts. First, we have a part for a straight step index fiber. And then we have the second part for the bent fiber. But I will start talking about the straight fiber. Now, the modeling workflow in comsol is that you most often start off by defining some parameters that are representing your problem. Like you can define the wavelengths and the frequency that is required by the physics and the solvers. You can define material parameters. For instance, in this case, we define the refractive index for the cladding and the core materials. You can define parameters that represents some geometric dimensions. And in this case, we specify the core radius and the cladding radius. So now that we have these parameters all set up, we can start building the geometry. And as this is a very simple model, we have one circle representing the cladding. So this is the big circle. And you see, when we define the radius here, we are using the parameter that we had defined up here. So this will be a parameterized geometry, which makes it very easy to change any of these dimensions if we want to do that. And then we have the second circle, which will be the circle representing the core. And again, we are using as the radius a parameter that we had defined up here. Now that we have the geometry, we continue and define the materials. So with the blue that you see, that is the cladding, and we use the parameter for the refractive index of the cladding to specify the real part of the refractive index. And similarly for the core, we are using the parameter for the core refractive index. So now also the material is set up here. So the next thing is to define the physics. And in this case, the physics is very simple. We have the default domain feature, the wave equation feature. So this node represents the vector Helmholtz equation that we are solving for all our domains of this problem. Then we also get by default a boundary condition on all the exterior boundaries. And the default boundary condition is the perfect electric conductor boundary condition. And what this says is that we set the tangential electric field components to 0 on this exterior boundary here. Now for this problem, this boundary condition doesn't matter so much what we use here, because we will be looking at modes that are confined to be located very close and inside the core here. So what we put here at the boundary doesn't matter much. Then we set up the mesh. And as you see here, the type of mesh that we will use is a physics-controlled mesh. And this is the standard type of mesh that you use. And what it means that it's physics control is that the physics will analyze the geometry and the size and the frequency component and the wavelengths. And then from that information, it will build a suitable mesh. So most often you don't have to work much with your mesh. You can just use this physics controlled mesh suggestion. But if you want, of course, you can build your mesh by adding any of the available mesh features that there is on the context menu. So now we have the geometry, the materials, the physics, and the mesh. And the final thing is to define the study. And we are going to make a mode analysis study. So what we need to insert here is the frequency we are working with, but also what modes we are interested in. So here we say that we are interested in modes that have an effective mode index that is close to the refractive index of the core. So yes, then we have everything set and we just click compute. And now we are down here in the result section. And what you see here is the mode field for the lowest order mode. And it is actually the Z component. So in this case, it is the component in the propagation direction that we see here. And here you also see what is the solved or the effective mode index for this mode. And with this arrow, we can jump between the different modes that we have solved for. And you also see that the effective mode index changes when we click these arrows. So these are the essential steps for making this kind of a mode analysis for a straight waveguide in 2D. Now we go over and look at the example for mode analysis in 2D axis symmetry or for a bent fiber. So I close this one too and I expand this one. So as you see, again, we have the geometry. And if I click it, you see that it looks a little bit different. And there are reasons for that this looks different. So let's first zoom out a bit here. So now you see that here is our waveguide structure, but here is the symmetry axis. So this waveguide structure revolves around this symmetry axis. So that is why we say that we have a bent fiber in this case. And now we zoom in again. So since we have a bent optical dielectric waveguide, this waveguide will actually be lossy. So we will have not only light propagating along the core, but we will also have some radiation that leaks out radially. And now then we must absorb that radiation. And to do that, we define perfectly matched layers, and we put them around the inner simulation domain. So now the radiation that propagates radially will be absorbed by this perfectly matched layer. And if we look at the materials, we see that everything is cladding material except for the core, exactly as for the straight fiber. For the physics, it is a little bit different, but not much different. We still have the wave equation representing the vector Helmholtz equation for the domain in this problem. We have an additional default condition for axial symmetry, because this is a 2D axisymmetric model. But since the symmetry axis is far from our simulation domain, we have no selection on that axial symmetry node. Then again, we have the perfect electric conductor, the default boundary condition on the exterior boundaries. But in this case, we decided to override it using perfect magnetic conductor boundary condition. So here we say that we set the tangential magnetic field components to 0 instead. But again, this boundary condition doesn't matter very much for this mode analysis, since the part of the wave that is leaking radially, it will be absorbed in the perfectly matched layer, so it will almost not reach this exterior boundary here. And then we have the mesh, and you see that we have a triangular mesh in the around the core and in the core, whereas we have a structured mapped mesh in the perfectly matched layer regions. And this is how you want to do it to avoid that you get very asymmetrical mesh elements in this perfectly matched layer region. And finally, we have to set up the mode analysis study step for this problem too. So again, the same frequency is used. Now the difference here is that when we now do this into the axis symmetry, the out-of-plane coordinates is no longer a spatial coordinate. It is rather an angle, the azimuthal angle. And thereby we have to insert, we have to scale the effective index of the modes that we are solving for with a characteristic radius. So this radius here, it's the radius from the symmetry axis to the center of the core in our 2D axisymmetric waveguide structure. But now everything is set up and we can again solve. And this is the result. So you see here the core boundary. And you see that the mode in this case, it is not centered at the center of the core, but it's rather pushed outwards radially. And what is also interesting to see is that if we go to the export node and look at an animation, we start this animation here. I hope you can see that you actually see that there is a wave propagating radially. So this bent fiber, it's leaking energy radially, and this energy is then absorbed by the perfectly matched layer. So with that short demonstration of comsol, you have seen two different types of mode analysis performed. One where we looked at a straight fiber, and one where we used 2D axisymmetry and simulated the bent optical fiber. So with that, I would like to switch back to the presentation. And after this demonstration, I want to provide a few more mode analysis applications. So in this application, we are interested in the mode fields for a microstructured optical fiber. And this microstructured optical fiber consists of a glass host, but there are 6 air holes inside this glass fiber. And because of the difference in refractive index between the glass and the air, the lowest order mode will be confined to the center of this fiber here. But some of the radiation can actually leak out in between the air holes here. So this is an intrinsically leaky fiber, although the leakage is very, very small. But it is important to be able to calculate how much loss you have in this fiber. So what this model does is to use 2 different techniques for calculating this low loss. Then this is an example of an optical anisotropic waveguide. And here we do simulations of both the case when we have transverse anisotropy and longitudinal anisotropy. And with transverse anisotropy, we mean that depending on the polarization direction in this cross-sectional plane, the wave will see a different refractive index. And with the longitudinal anisotropy, we will have a different refractive index depending on whether the polarization is in the propagation direction or in the cross-sectional plane. This is another example of a dielectric waveguide where we, in this part of the structure, have a slab, a fairly large slab with a high refractive index. And then also at the other side, we have a slab of high refractive index. But in between these 2 slabs, we have a very narrow region having a low refractive index. So what happens here is that if we think of the electric displacement field, the electric displacement field is the product of the permittivity and the electric field. And at the boundaries between different dielectric materials, the normal component of the dielectric, the electric displacement field is continuous. So in the material, the very tiny thin slab where you have a low refractive index, you have a low permittivity. And there, due to the continuity of the normal component of the electric displacement field, you must have a high electric field if you look at the electric field that goes in the normal direction to the field, to the boundaries. So in this case, we plot the electric field component in the direction normal to the boundaries. And as a result, you see that you get a large field enhancement. So this kind of a slot waveguide is one way of getting such a field enhancement. This is an example of a multiphysics model. So here we combine structural mechanics with electromagnetic mode analysis for a waveguide structure, where you at the bottom here have a substrate of silicon, and on top of that substrate you have a silica layer. And because silicon and silica has different thermal expansion coefficients, if you heat this structure up, you will mechanically deform the structure. And because of this mechanical deformation, you will induce stresses and strains in the material, and these will induce birefringence or optical anisotropy. And then we solve for the modes given that you get a different amount of optical anisotropy depending on how much deformation you have. So in this graph here, you see that when you don't have any stress or strain, that there are two degenerate modes. But as you induce more stress and more birefringence, the modes split and go to different effective indices. So now we have talked a lot about mode analysis. Let's talk about another optical waveguide simulation technique called beam propagation. And here the interest is to follow and see how a wave propagates along a waveguide structure. Now, to start off this discussion, we should say a few words about this beam envelope method. So this picture shows the electric field of a typical wave phenomenon. And since we are using the finite element method to solve this problem, we have to create a mesh that properly resolves all these oscillations. And that means that we need some 5 to 6 mesh elements per wavelength to resolve this wave phenomena accurately. Now, then you can understand that as we have 5 to 6 mesh elements per wavelength, when the problem domain becomes larger as compared to the wavelength, we will need many more mesh elements. So at some points we risk running out of memory, or that the simulation takes too long time to complete. But if we look at this wave, it is easy to imagine that we can write the total field as the product of a more slowly varying envelope factor times a rapidly varying phase factor. So now if we can guess what is the characteristic wave vector for our problem, then we can solve for this more slowly varying envelope factor instead. And the advantage, of course, is that we can use a much coarser mesh in this case. And not only that, the mesh is no longer related to the wavelengths of our problem. So we can solve for Gaussian beams propagating from Earth to Moon and back again without problem using this method. And for the remaining examples that I will show, we will in all these examples use the beam envelopes method. So this is an example of a directional coupler. So here we launch the wave in the right core of this dual core waveguide structure. But as the wave propagates along these two cores, the wave will start to couple over into the left core, and at the end of the waveguide structure we have almost all power in the left core. So this is the functionality of a directional coupler. This is not a typical waveguide example, I would say. What we have here is a slab of glass surrounded by air at the top and at the bottom. Then from this boundary here, we launch a Gaussian beam that propagates at an angle through this waveguide slab or through this glass slab. And because of the total internal reflection that you get between the glass and the surrounding air, all the power in this Gaussian beam will be reflected. So this beam zigzags along this glass slab here. So this is not a typical waveguide, it's more a light guide, I would say. Now this Mach-Zehnder modulator example I already showed you when I talked about waveguide parts. So what we have here is a Mach-Zehnder modulator. So on one of the arms in this interferometer part, we apply an electric field. And because of the electro-optic effect, we will then induce a change of the refractive index. So when the wave passes through this arm of the interferometer, it will get a different phase shift compared to the wave that passes to this lower arm of the interferometer. And when these two waves are recombined in this directional coupler, depending on the electric field we have applied here, we can control whether the beam will be transmitted through the top port or through the bottom port. So if we are only interested in how much light that enters here and exits through the top port, then we can use this as an amplitude modulator. But if we are interested in switching the field here between the top port and the bottom port, so sometimes it goes up here and sometimes it goes out here, we can use this for space division multiplexing. And finally, we have this optical ring resonator structure. So here we launch a wave propagating along the straight waveguide. But when the wave comes close to this region where the ring and the straight waveguides are very close to each other, part of the wave will couple over and enter and propagate through this ring. But then again, when the wave in the ring comes close to the straight waveguide, part of that wave will couple back into the straight waveguide. So in the second part of this straight waveguide, we have both one wave that has coupled just through this straight waveguide, but then we have the other wave that has coupled back from the ring waveguide into the straight waveguide. So these two waves, they interfere, and if we design this device correctly, we can make the two waves completely cancel out, so at a certain wavelength we can get zero transmittance through this straight waveguide. So that is why we call this a notch filter. So with that, I am ready for taking questions.
Well, thanks so much for that fantastic presentation. I'd like to invite Akhilesh Saladina to moderate the question and answer session. Akhilesh, take it away.
All right, thanks, Bonnie. So Ulf, we do have a lot of questions here, and I was thinking maybe we could start with the demo that you were doing, a couple of demos. So the first one is on PML. There are multiple questions on how to determine the thickness of the PML, and the other questions are on, like, can they use the scattering boundary condition instead of a PML? So maybe you could start with commenting on that.
Yeah, I can go back to the model here. And yes, for the PML that we have here, what is important to think about is that the thickness should represent a waveguide for the component of the wave that propagates in the radial direction. So since this is a mode analysis problem, most of the wave will propagate in the autoplane direction, but we will have a component in the radial direction. So we have to approximate that radial direction wave vector, and then the wavelength we get by taking 2 pi over that wave vector component. That will be the wave length in the radial direction that we should use here. And regarding the use of scattering boundary conditions, for the first part, the straight fiber part here you could use a scattering boundary condition. I can apply it here. And we actually have a special section here that is applicable exactly for the case when we do mode analysis. So if you check this checkbox here, then we again do this wave vector calculation. So we calculate the wave vector component in the radial direction, and we make sure that waves that match this wave vector in the radial direction will see this as a transparent boundary. So here we take into account that most of the wave vector will be in the autoplane direction. Now for the second case, you could also here use the same technique to use this setting for the scattering boundary condition. But you have more tuning possibilities using the perfectly matched layer in the 2D axisymmetric case.
All right. There are a couple of questions which may be related to the same thing, but maybe we can repeat it a little so that everyone is clear on this. So folks are confused about why the first model with a straight waveguide had like a circular cross section, and the bent waveguide has a square cross section. So why that extra layers were added? Maybe you can comment on that.
Yeah, I mean, for the straight waveguide here, this is, of course, this is how we want to make a simulation of a fiber. A fiber is something that is concentric. The reason why we treat the bent fiber and we build up this rectangular geometry here is because we want to apply the perfectly matched layers on these boundaries here. And it's better in that case to use this rectangular cross section, and then we use cylindrical perfectly matched layers for these boundaries here.
Right. Great. So the next question I have here is on capability. So can COMSOL model meta optics?
Yes, you can. You can define different types of geometries, different types of materials, and you can also do different types of topology optimization to satisfy a certain design criteria that you would like to achieve.
I see. All right. The next one is basically asking for a comparison maybe. So what is the difference between comsol's transient interface and FDTD method, finite difference time domain method?
Yeah, so the difference is that comsol is using the finite element method. And the advantage using the finite element method is that we can use a more general geometry. The FDTD method is very fast and robust, but it requires certain more rectangular shapes for the geometry.
I see. Great. So the next, I have a couple of questions here on a graded index waveguide. So the general questions are: can comsol model graded graded index waveguide, and how would we do it?
We can model graded index waveguides. So sorry, I clicked on the wrong thing. What we would do is to set up the materials here in the core, for instance. And when you specify the material here, you can not only say that it has a certain material, but the material property here can have a radial dependence or a radial function, so that you can get the radial shape of your graded material that you like to have. And what I was aiming at showing is that we actually have an app that demonstrates this. So I can load this. So in this app, this is the apps that I was talking about, that you can wrap a special user interface around a model. And as you see, you can here click on the graded index fiber, and then then you will have in this core, you will have the radially dependent refractive index. So this will become a graded index multimode fiber.
I see. Right. So the next one I have here is on a beam envelope method. So the question is, what is the best way to estimate propagation constant for beam envelope method in comsol?
So the best way to do this estimation is that most often when you launch or use some waveguide application, for instance, this directional coupler application here, you excite the wave using ports. And with these ports, you solve for the propagation constant. And then what you specify here for the beam envelope method is this propagation constant in the propagation direction. So that's is why I say that it's most often it's very easy to have a good estimation for what is your propagation constant or your characteristic wave vector.
Right. Can we analyze evanescent waves using this module?
Yes, you can, because we solve for the wave not only in the core but also in the cladding part where we have the evanescent tails. So
Right.
maybe I misunderstood the question, but in general, yeah, we solve for not only the core but also for the cladding part where we have the evanescent part.
Great. The next one is, can you set polarization of the incident waves?
Yes, you can. For instance, if we are working with the ports and you are using user-defined ports, you can directly specify it here. If we are using what we call numeric ports, so we are solving for the mode fields and the propagation constant, then what we have to do is that we have to solve for these modes and then inspect how do they look, and then we pick the proper effective index that corresponds to mode with the polarization that we like to have, and then we specify that here on the boundary mode analysis step here. So actually this model, the directional coupler, demonstrates how to handle the problematics of specifying the polarization.
I see. All right. The next question is, when, like in the demo, we showed mostly 2D models. So when we are expanding this to 3D, what other consideration should they make in terms of modeling strategies?
Sorry, could you repeat?
When you go from 2D to 3D, is there anything additional that the user should keep track of and take care of in modeling waveguides?
No, the principles are the same, and the use of this beam envelopes interface, it's also the same, that it's very important to get a good estimate of the characteristic wave vectors or the characteristic phase functions for the waves that you are solving for. In addition to that, I mean, there are no principal differences going from 2D to 3D.
All right, I guess we are running out of time. Maybe we can take one more question and then wrap it up. Bonnie, do we have time for one more question? Okay. All right. So, okay, the question here is on stress optical effects. Regarding stress optical effects on micro ring resonators, can I model acoustic stress using COMSOL?
Yes.
Maybe we need, yeah. Okay, maybe there was not enough information, like not very clear, but yeah, it sounds like we can do it. All right, I guess there are a lot more questions here. Maybe we could follow up with them, or if you can directly reach out to COMSOL, we'll be happy to answer them as well.
Great, thank you, Ulf and Akilish, and thanks to all of you for participating in today's webinar. Watch for an email from SPIE with the link to access the recording, and we look forward to seeing you all next time. Thanks so much.